So in this video, we're going to look at the anomalous Zeeman effect. So in the last video, we went through the spin of the electron, and a few things we looked at right here. We calculated what the magnetic dipole, orbital magnetic dipole was of the electron circling the atom, and it came out to be minus g sub L, which remember g sub L is 1, mu b, angular momentum over h bar, where mu b is EH bar over 2m, which is called the Bohr magnetron. It's a constant. And then we also had another magnetic dipole moment due to the spin of the electron. And that was equal to G sub s, where Gs was 2, at least that's what Dirac had said, mu b times the spin angular momentum over h bar. We want to keep them separate, so they're both angular momentum, but we want to keep them separate so we know which one is which. And we also have, just like we had with L, we also have S equals the square root of little s times s plus 1 h bar. But in this case, S can only be 1/2. And we also know that MS goes from minus S to plus S in steps of 1. So that really means that it can only be two values, minus 1/2 and plus 1/2. And then the Z component is m sub s h bar, which is plus or minus h bar, which is exactly what we had for our ups and downs. So first I just wanted to work out an example now. So now we have some state right here. And now we have four quantum numbers, n, l, m sub l, and m sub s. Okay. So suppose this thing is going to be, what, some radial function, which depends on the n and the l. And then it also has the y, the spheric harmonics, which depends on the l and the m sub l. That was your theta and phi component. And now we have the spin component. I don't know what to use, I'll just use that right there. And that depends on the m sub s. Okay, but this was a function. This is still a 1/2. So let's just say we're given some function, right here, an example. Suppose it's R21 times 1 all over the square root of 3, y10, and then let's make it the upstate, plus the square root of 2 over 3, y1 minus 1, the downstate. Suppose that was our psi right there. And now we ask, suppose you measure the energy. What are the possible values you could get right here? Well, energy only depends on the n quantum number, which is only dependent on this number right here, and it's all the same energy right here, so this is just E2 right here, which is just what, minus 13.6 all over 4, and that's the only energy. So this is the average energy. It's because it's the only energy you have right here, so we could also say this is the average. Okay, so there's the energy. What about L squared? What could you possibly measure with L squared? Remember, L squared is L times L plus 1 h bar squared, or L is the square root of that. We'll use L squared. Well, L is just, everything along here is just 1 right here. So it can only be one thing. L, little l, can only be 1. So that's 1 times 2, which is 2 h bar squared. So if I ask the average of that, it would also be 2 h bar squared, because it could only be that. What about L sub z? Well, L sub z is m sub l h bar. Well, that's just this number up here, and it looks like it can be two different values right here. It could be 0 h bar, so LC could be 0, or it could be minus 1 h bar, or minus h bar. Now the probability of being this one is what, 1/3. The probability of being that one is 2/3. So if I wanted to get the average LZ, 0 times 1/3 plus minus h times 2/3. So that's just minus 2/3 h bar. So there's the average of that one. What about if I wanted to measure S sub z? Well, if I put S sub z, this is just my upstate right here. If I measure S sub z, I'm going to get h bar over 2. That's one thing I could get from SC. Or I could measure the downstate and get minus h bar over 2. The probability of this one is 1/3. The probability of that one is 2/3. So if I wanted to get the S sub z average, it'd be 1/3 h bar over 2 plus 2/3 minus h bar over 2, which is equal to h bar over 6 minus 2h bar over 6, which is minus h bar over 6. So that would be the average S sub z. Suppose we wanted to find the average of S sub x right here. Well, I'd probably have to turn this into rights and lefts right here. So now you'll notice when we do the S here, the R's and the Y's don't even matter right here. So I could have just turned this into 1 over the square root of 3 up plus the square root of 2 over 3 down. And then I could have turned my ups and downs into rights and lefts, just like we did before. So the other part doesn't even matter on this. So this would just be, 1 over the square root of 3, and then we would turn that into 1 over the square root of 2 right plus 1 over the square root of 2 left plus the square root of 2/3. And this would be the square root of 1 over the square root of 2 right minus 1 over the square root of 2 left. Okay, and then we could have factored out the rights. And you'd have 1 over the square root of 6 plus the square root of 2 over the square root of 6 plus left 1 over the square root of 6 minus the square root of 2 over square root of 6. Oh, sorry, I already pulled the left in there. Okay, so then all I'd have to do is, if I operated Sx on this, it's just going to give me h bar over 2. So the thing I can get is h bar over 2, and when I apply Sx on that, I get minus h bar over 2, and the probability of this one would be this squared, so it would be 1 plus the square root of 2 squared all over 6, and this one would be 1 minus the square root of 2 squared all over 6. And the average would be this times this plus this times this. So the average of Sx, I can pull out the h bar over 12, h bar over 12, and then we would just get this minus that. So we would have 1 plus the square root of 2 squared minus 1 minus the square root of 2 squared. Now this inside would give me 1 plus 2 square root of 2 plus 2. And then over here, this would give me minus 1. And then the middle term would be minus, but then I make it plus 2 square root of 2. And then the last term would be 2 minus. So the 2's are gone, the 1's are gone. So this is just 4 square root of 2. So this would be h bar 4 square root of 2 all over 12, which is h bar the square root of 2 all over 3. So that would be s sub x, right? And we could have done s sub y or whatever we wanted right here. Okay, so now you can see the full wave function comes all the way out right here. Now, also on the last video, we went through something called the normal Zeeman effect, which was when we put our atom in a magnetic field, it split the lines right here. Evenly split. They were all evenly split. Now, but we said, you know, there's another effect called the anomalous Zeeman effect, and that splits the lines too, but this one is much more normal. This one should have been called the normal Zeeman effect, because for this one, we get the Zeeman effect even without an external magnetic field. So what does this anomalous Zeeman effect do to? Well, suppose we look at the atom right here. Again, when I draw it, I have to draw it, you know, as like a particle. Remember, it's not really a particle, but so what do we have? I'm going to look at it from the electron's point of view. Here we got this electron right there. What does the electron see? He sees the proton going around him. So here is the proton right there going at moving around him. So the electron, and we know that a circulating proton makes a magnetic field right there, just like a loop of current. And so there is already a magnetic field on that electron. And so this electron, this spinning electron, is already in an external magnetic field. The external magnetic field is due to the proton. Remember, we said the dipole moment, the energy due to a dipole was minus, mu, and in this case, it's the spin. This guy's the one that's spinning. He's the one that the magnetic dipole, dotted with the B due to this going around. So this is the B due to the proton right here. So he's always got it there. Also, mu s, remember, we already wrote down what mu s was right here. It was minus gs mu b s over h bar. So I'll just rewrite it here. This mu s is equal to minus g sub s mu b s all over h bar. Okay, so I can put this up into here, and it looks like the two minuses will drop out, and we'll get a plus. So mu sub s is equal to, it's going to be, putting that up into there, it's going to give me a plus g sub s mu b over h bar, and then we're just going to get s dot b. Okay, so sorry, that's the energy right here, not the mu s. We're plugging this up into here. That's the energy of the dipole, u sub d. Okay, so now all we have to do is calculate what the B field is right there due to that spinning proton right here. So we have to go back to, if you remember from electromagnetism, the B due to a moving charge is mu naught over 4 pi. It was Q V cross R hat all over R squared. So hopefully that by Savar's law looks a little familiar. In this case, Q is the charge of a proton, which is just E, so I'm going to put in E right there. And okay, so, and I'm going to do a few things. We know Q is equal to E, the charge of a proton. We also know, I'd like to put mu naught in terms of epsilon naught. We do know that epsilon naught mu naught is 1 over the speed of light squared. So mu naught is equal to 1 over epsilon naught c squared. So we know that. And also, that R vector, that R hat, I'm going to turn it into an R vector over the magnitude of R. Remember, that's the definition of R hat. It's the vector R over the magnitude. This thing really had a magnitude of 1. Okay, so if I put those three things in, we get B equals the mu naught becomes 1 over 4 pi epsilon naught c squared and then we get the Q, which is E. Just put it right in there, E. And then we get a V cross R all over R cubed now. V cross R all over R cubed. Okay. Well, we also know that the electrical force between these two, Coulomb's law, is just E squared all over 4 pi epsilon naught R squared. So there's the force. And that's also equal to minus the change in U. Remember, the force is minus the derivative of U with respect to R. Well, I notice I have a 4 pi epsilon naught. I'm going to pull two of the R squares out over here, and I need another E up there. So I'm going to put an E in here. I'm going to put in another E here, and I'll put another E down below. And I'm going to pull two of the R's over into here. So this right here would be the force, which is given by that. So B is equal to, it's going to be a minus. We've got all this part right here. We got minus du dr. What's left? We still have c squared and another E down below and another R. C squared, E, and an R. And we still have the cross product, V cross R. Actually, I think what I'll do is I'll switch the order. Instead of V cross R, I'll make it R cross V. If you swap the order, it's a minus. It changes the sign, which would make this a plus. And I'll make that R cross V. Okay, so there's the B so far due to that. And then we also know that the definition of angular momentum, we like to put everything in terms of angular momentum because it's something we can measure. L is equal to, the definition is R cross P, which is R cross MV. Or I can pull the M out in front, that's just M times R cross V. So R cross V is just L divided by M. So I'm going to replace this with L over M. So we get B is equal to, I'll put this stuff here first. 1 all over c squared E R du dr times r cross v, but r cross v is L divided by m. So we've got an L here, and I'll put the m down below. Oh, that's nice, mc squared. Okay, so this is the magnetic field. And so now I can take that magnetic field and put it back right up into here. So we'll put that magnetic field right there. And we got U is equal to G sub S mu B over H bar. And then we still get this stuff, mc squared ER in the bottom. mc squared ER du dr. Okay, and the only thing left is, since we're plugging this in for B, we get S dot L. S dotted with L. Okay, now, so this would be the energy. Now, thing is, we did this from the point of view of the electron. Remember, in the real atom, the electron's going around the proton. It's the proton that's the heavy one that's not doing much moving right here. So what we really need to do is convert it back into the proton's frame, not into the electron's frame, which requires a Lorentz transformation. I'm not going to do the Lorentz transformation, but this transforming it from the electron back to the proton, all it does is make that twice as small. It puts a 2 in the denominator. It's something called the Thomson precession. Thomson precession. You can look that up. All it's going to do is it's going to go from the electron's perspective, electron's frame to the proton's frame. And all it does was it divides this by 2. So that means U is really just G sub S. Okay, even though G sub S is 2, it'll cancel that 2, but we'll keep it in there. Mu B all over H bar. We're going to have a 2 now. Again, that's due to that Thomson precession. mc squared ER du dr S dot L. Now, you can see this is the orbiting electron with its own spin right here is really what we're looking at. And we call that spin-orbital coupling. These two couple together. We call it spin-orbit, because you're really looking at the two. Spin-orbit coupling. Coupling. Okay, so what that does is that the two couple together. Now, when we looked at without spin-orbital coupling, when we looked at the L, we said we had some L. When we put a magnetic field, let's say in this direction, we had L going like this, and L was orbiting around like that, which meant the magnitude of L was a constant, and the Z component was a constant. So L and L sub Z was a constant. Also, when we had, with the spin, we had say some S, and S was also orbiting around, and so the magnitude of that S and the Z component was also a nice constants right there. So what did that mean? That meant that M sub L in m sub s, because remember s wasn't, we don't really call that a quantum number because it's only one number. M sub s were good quantum numbers because these things don't change. They're constants right here. But that's without spin-orbital coupling. When you have spin-orbital coupling, these two couple together right here. And so what we have now is we have, say, L is going off like this. And it doesn't go around like it did before. And we also have S. Let's just put S right there. S. S again doesn't go around like this. If you look at the total angular momentum, if I add this vector onto that vector, the total would be right there. That vector would be L plus S. L plus S. What happens is that these two orbit this vector right here. So they kind of go around like this. So they're on up, and it kind of goes around like that, so that the total goes out there. It's the total that's fixed, and it's the total that goes around right here. So this is how these two couple. These two are going around, and they're slowly precessing right here. So you notice L isn't, we don't want to use that as a good quantum number, at least LZ, because, you know, it's just not going around like this anymore. It's kind of going like that. So what we'd like to do is we would say, why don't we call J the total spin angular momentum, which is L plus S. And it's J that's going to stay. That's a good one we want to use here is J, which is L plus S, plus the Z component of J right here, because this right here is the Z component would be right there. So it would be J sub Z is what we want. These two right here. Or we still want to use the L in there too, but so we got J sub Z is just, these two are the ones we want, which is just L plus S and the Z component. Okay, well, so now, what do we have? Now, if we just go back to all of ours, what did we say? We said before that L is equal to H bar times the square root of L times L plus 1. We also said S was H bar times the square root of S times S plus 1. Here we said L could be what? 0, 1, 2, dot, 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 dot. Here we said S can only be one value, 1/2. But now we're going to also have J. And J is equal to H bar times the square root of J times J plus 1. Okay. Likewise, we had L sub Z is equal to M sub L H bar, where M sub L went from minus L, and then you added 1 to it, minus L plus 1, all the way up to plus L. Then over here we had S sub Z is equal to M sub S H bar, where M sub S goes from minus S to plus S. Minus S plus 1, just like this one, but there's only two values. I'll write it as minus S plus 1, dot, 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 all the way to plus S, but there's only two values, minus 1/2, 1/2. And then over here, we can say J sub Z is equal to M sub J H bar, where M sub J goes from minus J plus 1, dot, 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 all the way up to plus J. So what used to be our four quantum numbers, actually this was N, L, m sub L and m sub S, when you have spin-orbital coupling, the good quantum numbers are N, L, J, and m sub J. Those become our new quantum numbers right here, because L we care about is what is the total angular momentum right here, because it's the, whenever you apply a torque on, it's always the change in the total angular momentum. Okay, well, the only thing we don't know the range of, we know the range of L goes from 0 on, and we know m sub L goes from minus L to plus L, and we know everything about the S, what it goes from. The J, we know what m sub J goes from, but we don't know what J is. What is the range of J right here? So that's what we need to find out. What is the range of J? So, first of all, we do know that J sub Z is equal to L sub Z plus S sub Z. Well, J sub Z we said was m sub J H bar equals m sub L H bar plus m sub S H bar, or we could get rid of the H bars here for a minute. But suppose we wanted to know what is the maximum m sub J could be. M sub J, the maximum it can be, is equal to what's the maximum m sub L can be? Well, from right here, the maximum it can be is L. And what's the maximum that m sub S can be? Well, it's 1/2. So there is the maximum of m sub J. Well, we already said over here that the maximum of m sub J is J right there. So this is J right here. Now, so it looks like this. J can be L plus 1/2. Okay, and then it could be, well, then it could be 1 less right here. So remember, this thing goes down this way right here. I don't know how far it goes this way. So it could be L minus 1/2, L minus 3/2, dot, 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 dot. I don't know, where does it end? That end I don't know. So where does it end? Where does it end? Okay, well, suppose we look at our vector right here, J. Let's look at it right here. Suppose for a minute that this is your L, and suppose S is just going out further. Suppose there's your S right there. So this right here is the magnitude of L. This right here is the magnitude of S. And this would be, since they're just end to end, the total length is just this length plus that length. So L plus S, and for this case, the magnitude of it is just the magnitude of L plus the magnitude of S. Sorry, that equals the magnitude of L plus the magnitude of S. Okay, well, suppose they aren't end to end, like, well, not in a straight line. Suppose L was going like this, and S is off in that direction. So this one is still your L, this is still your S, this length is still your magnitude of L, and this length is still your magnitude of S, and this would be L plus S. Now, this length right here, this length is shorter than this length right here. So the magnitude of L plus S is less than this, because this length is that long, this one's shortened right here. So this one is less than magnitude of L plus the magnitude of S. Plus the magnitude of S. Magnitude of S. Okay. Well, let me just keep swinging. I was just swinging this around. Why don't we swing it all the way around so that it's right at coming back down? So here is your L, but now my S is coming this way. Okay, so now we've got this one right here, and now we could say this length right there would be the magnitude of L minus the magnitude of S. So this length is the magnitude of L minus the magnitude of S right here. Okay, and that's what, so this, we have to add the two vectors, L plus S right here. Okay, so you notice all of these were L plus S's, this one, and this one. But this is the longest it can be. This is some intermediate length, and this is the shortest length it is. So in general, this length is greater or equal to this right here. So in general, this length is L plus S magnitude is always got to be greater than this because this is the shortest it could be. So it's got to be greater or equal to the magnitude of L minus the magnitude of S. I should put another magnitude because I don't want this thing going negative on me, because if this was bigger than that, I just want to know the magnitude of everything. Okay, so this right here, L plus S is J, and so this is going to tell me J has to be bigger than something, which is what I wanted, because remember, this is the biggest and it gets smaller and smaller, but now I'm going to get some N to it right here. Well, so this is just my J, and so if we plug in, we get the square root of J times J plus 1 H bar. I'm going to get an H bar in all three terms, so I'm just going to cancel those out. That's greater than or equal to the magnitude. Now, the magnitude of L is the square root of L times L plus 1 minus the magnitude of S, which is the square root of S times S plus 1. Okay, so this is saying that J is going to have to be bigger than this right here. So on the next lecture, we'll try to we'll figure out from this where this sequence ends right here. Okay, so just remind you, now we have got new quantum numbers. When you have spin-orbital coupling, we have these right here instead of these over here. Okay.